is Clément Lagisquet from l'Université Savoie-Mont-Blanc, and he's going to talk about Markov numbers, an answer to 3 conjectures from Aigner, or something like that. Please, Clément. Thank you. So my talk will be about Markov number. It's a joint work with Edita Pelantova from the ZEC Technical University and Sébastien Tavenas and Laurent Villon, which work in the same laboratory as me. So here's the outline of the talk. So we'll start by defining the Markov number, the Aigner conjecture, and then introducing our tools, so the M value and transformation on path. And then we'll conclude. So what are Markov numbers? First, we will need to define Markov triples. So there are the positive integer solution of the Diophantine equation x squared plus a squared plus z squared equal true x, y, z. And the first one are 1, 1, 1, 1, 1, 2, and 1, 2, 5. So we will see next that apart from the two first one, there is no repeating number in the triplets. And we will call the maximal value of each triple the Markov number. So here we have 1, 2, and 5. And a conjecture from Frobenius is that each Markov number is the maximum number of an unique triple. And it's standing since 1930. And we can construct the Markov number by some recursive construction. If you have a Markov triple, L, M, and R, you can get two new Markov number by this formula, which are quite symmetrical, if you see. And with that, we can construct a tree, which we call the Markov tree, and we have all the triple 1, 1, 2, 1, 2. And each time the Markov number is the greatest of all. And this tree can be identified with the Sternbroker tree, which is this one, which is constructed as a binary tree from the Farey fraction, which are defined like this. And so, as I said, all the Markov number greater than 5 can be identified with the Farey fraction in the Sternbroker tree. And we will now refer to each Markov number by the Farey fraction which is associated with it. So we call them M, P, Q. So for example, M12 will be 5, etc. In his book, Martin Aigner states 3 conjectures in order to better understand how the Markov number behave. So the first one is the fixed numerator conjecture. So if you have P, Q, and A, all integers, A strictly positive, P less than Q, and P and Q relatively prime, and the P and Q plus I relatively prime too, then we expect that M, the P over Q, is less, strictly less than P, M, the P over Q plus I. So the fixed denominator conjecture is quite the same, but we work on the numerator. And the fixed sum conjecture, you take P and Q and I, again integer, PQ relatively prime, and this time P less than minus A, Q plus A, relatively prime 2, and we expect that M, the P over Q, is less than M, the P minus A, P plus A. And the first one of this was proved last year by M. Rabideau and R. Schiffler in this article. And their proof was quite technical and based on the perfect matching of snake graphs. And so we try to improve their proof and apply it to the two other conjectures, and it works. So we will introduce our first tool. So if we have a word on an alphabet of 2 letters, we choose A, B, then we can map it to some matrix in SL2 to Z, with A being this matrix 1, 1, 1, 2, and B being this matrix 2, 1, 1, 1. So if we have a word like this one, we obtain this matrix. And we have some property on those matrices, which are quite useful for proof. If you have the U, this matrix, 0, 1, minus 1, 1, 0, we have AB minus BA, which is 2U. And AUA equal U, BUB equal U. And the most important one are AUB is this matrix, which is non-negative, and BUA, this matrix, which is non-positive. And we can associate to each word a value through the map MW equal 10.MW01. So we will take the upper right coefficient in our matrix. So for example, M, the AABA will be 17. The M value was chosen because it's an extension of the Markov number, as we will see later. So if we take a line from 0, 0 to QP, and we discretize this segment, we construct what we have, we call a path associated with a Christoffel word. So we have those two conditions. We stay below the line segment, and there is no integral point between the line and our path. And we can associate to each path a word, which is obtained by replacing each horizontal state by A and each vertical state by B. So here we have this word AAB, AAB, AB, which is the Christoffel word, the lower Christoffel word, because we can define an upper Christoffel word by going above the line, C35. And we extend this definition. So if we take the M value of this word, we will get 433, which is the Markov number associated to 3/5. And when we have the Christoffel word associated with 3/5. And so we had a problem because sometimes we have N and D which are not relatively prime. So we extended our definition naturally and got some power of a Christoffel word. If you see here, you have AAB power 3, and AAB is a Christoffel word. And we can associate M value to all of those words. So here is are the M value for N and D in 0.6. And in red, you have the Markov number. So you can see when you have N and D relatively prime, you will have a Markov number. So we have some property on this, like asymmetry around the diagonal. And here you can look at some Fibonacci number, even indexed, and here the odd indexed Fibonacci number. Here we have the Pell number with the even indexed one here and the odd indexed one here. So the main idea of our work was to use transformation in order to get a chain of monotonous inequality on the associated M value. So the idea is here in a visual picture. So if you have a 5 tree, you want to go to 7 tree, but you must first go through 6 tree. So it was why we needed some extension of the M value. And we have the same for fixed denominator and fixed sum conjecture. So we define some flip, which are when you have AB and transform that in BA. So you reverse a square if you want. And we add some inequality and some case of equality. Visually, it's this. So if you go from the blue world to the red world, the purple part are the same. So here we have an equality on the two m value. Here it's less than this one. It's still less and still less. And so we obtain this chain of inequality. So MBBAA is greater than M the AABB. But it wasn't sufficient because sometimes we needed to have two flips together because if not, our chain of inequality were not in the same sense. So it was a big issue. So we defined this theorem lemma, which is quite the same as the previous one with z equal to 0 in the previous one. And we have quite the same structure. And visually, it's this kind of difference. So here, the path, which is purple and blue, is greater than the one that is purple and red. If you go to by the m value, it's the reverse in those cases. This one too, and here is the equality case. We have another useful definition for proof, which was the packet set. So a packet set is something like that. You cannot have an all. If you start a column, you must go to 0. And if you have a column here, next, you are obligated to be at least the same 8 on the right. And with that, we can define the below set of a word. And the hull of a below set was a word, a path. And we have a bijection between the packet set and our word on two later. And with something on the Christoffel and pseudo-Christoffel word when we use the triangles. We define the flattening of a below set. You have a line and you don't want anything above the line. So you remove the green dots. And you can do the same with word. So here, with this word in blue, you get this word in blue and green. Here, delta W is the algebraic vertical distance, which is this complicated thing. And what we obtained was that the flattening of a word was less, the m value of the flattening of a word was less than the m value of a word. And the equality stands only if the flattening is the word. With that, we can prove our first conjecture. And the idea of the proof is this one. If you have a word, which is the purple and blue one, so the m value of these things is greater than the m value of only the purple part. And the m value of the purple part is greater than the m value of the flattening of this part, which is the m value of the Christoffel path ND. So, and for the fixed denominator conjecture, we use some symmetry arguments in order to obtain the proof. After the flattening of a word, we use the lifting of a word. So we start by a packet set, and this time we want to pack under the whole line. So we add these green dots. And it extends on a map to our world. And we obtain from this path, this new path, and the associated world with it. And with all of this, we can prove that the M value of the lifting of a world is less than the M value of a world. And it helps us to prove that the M value of the world is always greater than the M value of a Christoffel world. And so we have a kind of minimality of the M value associated to the Christoffel world on these things. And we have the case of equality, which is this expression. And with this, we can prove the fixed sum conjecture. And the idea is this one. You have a world which is in orange here, which is the lifting of the world in purple and red. So we can apply our lemma and say that the M value of the lifting is greater than the M value of the world, and the M value of this world is greater than the M value associated with the world in blue, which is the one associated with the Christoffel path and D+1. So getting everything together, we have this formula, this chain of inequality that say that our world MCN+1 D is less than MCN D+1. Okay, so in conclusion, if you have a Markov world P over Q, you can you have all the Markov world in this region here in red that are greater than him, and all the world in this region blue, which are less than this than this one. And in order to prove the Frobenius conjecture, we only need to look at these two regions in gray. So thank you for your attention. And I have put in the slide some reference if you want to read on that.
Thank you. Do we have any questions for Clément? Yes, someone raised their hand, but I don't see who. Christophe, yes. Please go ahead.
Hello, do you see me? I don't see me, but
yes,
thank you for this nice talk. I have with Mélodie Lapointe, we have recently published, I think it's published, a related work, which is also, it is also particular cases of the Frobenius conjecture with inequalities between Markov numbers and generalization also. We generalize the mapping. We associate to each Sturmian, finite Sturmian word a number. And so the conjecture we have is that it is still injective, but it's a little bit difficult to compare because we don't use the same cone matrices as you you use the two cone matrices which are symmetric, 2, 1, 1, 1, and the other is 1, 1, 1, 2. And we use a 2, 1, 1, 1 and 5, 2, 2, 1. And it's known, it's in the book of Aigner that both of them may be used to compute Markov numbers. I don't know how it compares to your mapping. I mean, you have a it's the same idea to extend the function to other words and to to generalize the conjecture and then prove particle cases of this due conjecture.
Yeah.
This is the same idea. The paper is called On Frobenius Conjecture.
Yes, I read it.
Yes, you have it. And
yeah,
second thing I wanted to say is that I just last week, perhaps you have got it also, I just got an email from some Korean mathematician who claims that, who has written on Archive a note where he says that the proof by Rabideau and Schiffler is not correct. And I didn't look at the details, but perhaps you have got it.
Yes, I also had an email from this Korean scientist.
His name is Do-Young Kwon.
Yes, exactly, it's this one. I didn't look in detail on his argument on what Schiffler and Rabideau did, but they also had another article which was published a short time after was on the tree conjecture, where they used cluster algebra in order to prove the conjecture. And contrary to us, they have a nicer slope here, where they can say something on the Markov world, on the ordering. And there is also another one from, I don't remember his name, it's Greg something, I believe, which use a distance on the, where you can prove that the Markov number are, the tree conjecture from Aigner are proven. Mm-hmm. But for what I remember, your matrix B, the one that use to map B to some number, is AB. It's the, or something like that from Urs. I'm not sure, but I believe it was something like that. If you take AB, it's quite similar to yours.
But do you obtain the same set of numbers?
No, because we don't have. If you map out the B, we will need to map the AB to the matrix 5, 3, something like that, in order to get the Markov number. If it's like the L shape is related to that. But it was easier for us to only look at these two matrices, which fit quite nicely to the path that we define.
Okay, thank you. I have finished.
Thank you, Christophe. Anything else for Clément? Any other comments or questions?